Okay. So, this lesson we'll talk about the frequency domain, which means that we will talk about the Fourier transform, wavelet transform, to enrich your data representation in your neural network application. Okay? And so normally we have some basic data. For example, if we have the training data, we have the input and output, but maybe your input is in the dimension of the 4. Okay? And so we have four separate or the distinct data to represent your outputs. Okay? But if we can use the Fourier transform or the wavelet transform or any other mathematical transformation, we can increase our input data by using the 4 distinct data which is given in the X. Okay? And so we can increase the input feature by using these functions or this transformation up to, for example, 100 distinct data. Okay? And so in this lesson we will talk about it. Okay? Firstly, we need to give some basic information about the Fourier transform. Do you know about the Fourier transform? Have you seen that, or have you write the written code about the signal and system or the processing techniques? Okay. The Fourier transform is created by the Joseph Fourier in 1807, and it's the fundamental theorem to function representation. In frequency domain. Okay? Normally we have the time series data in real life application or real time application, but by using the Fourier transform we can convert the whole time series data into the frequency one, and so we can generate some other properties from this signal by utilizing the Fourier transform. And so this Fourier transform can be given with the basic representations of the fx with some constant value in order to represent the bias value in your neural network application. And so we can represent the whole data like this one, ak times cos kx plus bk times sin kx, etc. Okay? And so any function can be modeled by using the infinite series of the cosinus and sinus. What's the importance of the cosinus and sinus? These components creates the frequency characteristics, right? Because if we have any data which is given in in this function form, the equation form, and so we can create some frequency pattern or the sequence pattern with the previous one or the next one. Okay? And so we can define the frequency characteristics like using this one. And so this A0 can be obtained with some basic formula like the 1 2 dot pi period in here, like this one, fx and dx, and bk can be created with the 1 pi 0 to pi fx times sin kx dx, or ak can be obtainable with the 1 divided by pi 0 to 2 pi fx times cos kx and dx. Okay? This is a simple formula to create your infinite series from the Fourier transform. We don't need to underlying mechanism of this pattern or the foundation of this problem, but if you can use or if you can calculate these coefficients, and then we can represent this, for example, signal like like we can represent this square signal by using the infinite series of the cosinus and sinus theorem. Okay? For example, if we apply the Fourier series or transform, and then we can create this pattern. What's the difference between the blue line and the black line? Huh? No. So this is the infinite series of the Fourier components. This signal, the black signal, cannot be differentiated. Which means that this discontinuous property is included in the black line. But if we have the infinite series time values or the signals or the equation to represent the square signal, and then we can manipulate these values in terms of the frequencies or the amplitudes or some different form of equations. Okay, this is a huge advantage to create your pattern or your formulation to create the input data set in your neural network application. Okay, and so if we have this kind of information, and then we can move to the first example in here. Firstly, we need to open this code like this one, and then the first example to create this Fourier series. Okay, so firstly, 0 Fourier series dot pi must be given in here like this one. Okay, and so in order to model your properties or the function, we can use the import numpy library as MP and import matplotlib.pyplot as PLT. Okay, and so the second term is related to the visualization of your data set. Okay, firstly, we need to give some function definition to create your pattern. Okay, function definition. In order to build our model, firstly we need to create the square wave by using the t time period, frequency, and amplitude value with the initial values of the 1. Okay, and so we can return to the amplitude times 1 plus MP sine. What's the meaning of the sine? We can create the 1 and 0 values by using this function. Okay, and so we can create the square function by using these terms. Okay, and so MP dot sin 2 times MP pi times frequency times t. Okay, and after that we should divide the values of the 2 because we want to our signal to the between the range of the 0 to 1. Okay, this is standard representation of the MP sine and MP sinus function. Okay, after that, how can we create the Fourier coefficients in here? T signal and num terms. Num terms means that we can create the Fourier series at the infinite time, but some of the components are meaningless in here. And so if I check or if I choose the num terms, for example 10, and so 10 iteration or the 10 function is created to represent the R square waveform. Okay? And so, how can we calculate these values in here, like this one? I can create the list in here for n in range of the num terms. Because we have the 10 function, or the 5 function, or the 20 function, right? And so, an is equal to the what? 2 times np trap is the integrate along the given axis using component trapezoidal rule, which means that we can take the integral values of the what for the proposed values, which is given in the what in the slides, right? And so the signal times np cosinus 2 times np pi times n times t, okay? And we should give the t values, right? Because we have some periods, and we can generate the trapezoidal rule in order to be applied on this value to get the integral value, so the total area, which is beyond the what these signals, okay? Trapezoidal rule means that we can create the some iteration rule to get the integrate the hard terms. For example, if we have the sum continuous function, we can generate or we can calculate the sum analytical form. But if we don't have any analytical form, we can discretize all the terms in the what by using the some basic function. One of them is the trapezoidal. Okay? We can use the square form, but trapezoidal is the best way to create this pattern. Okay? And so Bn is calculated with the sinus term, because in our formulation, this one, and also we should give the what coefficients that append must be given as a tuple values in here, like this one, an and bn, and after that we should return to the what the coefficients, okay? And so if we have the signal put into the what to this function, and so I can generate the what the an and bn value to represent the R signals, right? Okay. So we want to reconstruct the R signal by using what? These coefficients, okay? And so T and coefficients must be utilized in this form, okay? And so the signal should be created in here, zeros like T must be given in here, and individual terms is created for the what? For N, and AN and BN, right? In enumerate for the what? The coefficients, right? Because we have the in this and AN and BN stored in the what? In the coefficients. And so I can reach the these values by using the enumerate function, okay? And then the term is equal to the what? The AN times MP cosinus 2 times MP pi times n times t plus Bn times MP sinus 2 MP pi times n times t, like this one, right? The term is given in here. And what? Yes, I'm coming here, but we don't have the A0 in this case, because we don't have the some bias value, okay? If the A0 must be calculated, and then we can put the another term in here, just like that, okay? And so individual terms that append must be given in here. This individual terms is defined for the what? For the visualization of the whole of the signal in the one subplot, okay? Otherwise it's unnecessary for our signal. But in order to create this pattern, minus plus equal term must be collected like this one. Okay, right? So after that we can return to the signal and the individual terms. Okay, so these are the functions, and after that we should give the main code in here. Main code. Okay, firstly we need to define the parameters like this one. For example, frequency pattern is 1 and duration is 1, and num terms in the first place, for example 2. Okay, and we can generate the data set in here like this one. T is equal to the mp lin space with the values of what 0 to duration values, and 1000 values is included in this case. Okay, and so endpoint false must be given, and square wave signal can be created using the square wave signal, and so T and frequency values can be given at this time. Okay, this generates to the square signal. Okay, no, so we generate this instead as a default values. Okay, but you can do that, and after that we must get the coefficients values from this term like this one, Fourier coefficients T, and square wave signal R signal in here, and num terms is the iteration number, and so this creates the coefficients. Okay, and after that we can use these coefficients in order to reconstruct the R signal on the time domain. Okay, and so reconstruct the signal and individual terms can be assigned with the reconstruct signal parameters in here like this one, T and coefficients. Okay, any question? This is the simple example for for our chords, and so in order to show every pattern in this domain like this one, demonstration, and so firstly we need to give the PLT figure with the fixed size 12.8. Okay, and so PLT subplot can be utilized with 3, 1 and 1, and PLT plot T and square wave signal, and we have the label values in here, original square wave. Okay, and after that PLT title can be given with the original square wave signal. Okay, and PLT X label can be assigned with the time, and Y label is the amplitude. Okay, AMP. So PLT subplot 3, 1, 2 and term in enumerates with the with the individual terms like this one, and so in each case PLT plot T and term is given in here like this one, the label of F and term n plus 1. Okay, and so if we have the 10 terms, and so this subplot contains all the function sinus and cosinus. Okay, so PLT title is the watt, sine and cos values, okay, and X label and the Y label is the same, okay. After that, we can create another subplot in here, 133, okay, and plot the reconstructed signal like this one, and so label is equal to the watt reconstructed signal, okay. These are the codes, PLT, right, and the other terms are the same with this notation, and so reconstructed SV time and this amplitude, but PLT legend should be called in order to visualize all of these things, and tight layout and PLT show must be given, okay. And so if I run this code, and then we will have this signal like this one, okay. This is the original signal, this is the two sinus and cosinus values, okay, but the constructed signal is not like to what, to square wave, right? Okay, but if I increase the num terms in here like this one, for example 10, if I rerun this code, and then voila, this is something like the square form in here, and the whole forms is a collection of the what, the second figure, right? It's clear? Okay. And so what about the 100 values? See, it's getting the warm to the watts to these values, right? And what about the 1000s? See, this is the square wave like this one, but this is important for the neural network application because we have the square wave in here, but we have what, 1000 different features from the one signal. You get the picture? If you can do that, and so we can create another representation by using total 1000 different feature vector. This is a huge advantage for the what? For your application, right? Okay. This is the what? This is the one signal. If you only use this signal to train your neural network or any other algorithms, and so then maybe it's useful. But if it does not, and then we can use the Fourier series to what? From the one signal representation to 1000 representation, because the collection of this term is what is linear, and so we can add the whole terms, and then we can get the reconstructed signal with a different way, with the same way. Yes. 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 This is the advantage of this term. And so if you had the A0 term, and then this values is more accurate. Okay? Any question? Okay. So this is the first example. And then what? if we have these terms, and then we will continue with the what with these terms. If we know that this representation, where's my pen? Okay. If this representation generates the what, the one feature to the what, the 1000 feature with the same characteristics, right? And so this is 1000 vector, but this is 1 times 1. And so this is more accurate and more informational for the what, for your application. You can generate the what, or you can enrich your data set by using these terms. Okay? So what about the Fourier transform? This Fourier series, but in this case we will talk about the Fourier transform. Fourier transform is the transformation technique that decompose or separate or distinct or the split a function of time into its frequency components. Okay? In continuous function, we have this integral like this one. X f is equal to what? Minus infinity to plus infinity in here, and we can give the xt time series signal in here like this one, and so exponential over j to pi f and t can be given in this integral. And so if we can calculate this integral, and then we will get the what, the frequency pattern of these terms. But this integral is important because this is our signal, right? But this is our the convolutional operator. In the previous lesson we talked about what the sharpened image blurred filter or the kernel function. And so if we have this kind of kernel function, and then we can create the what, the frequency pattern. This is simple, but this is special convolutional operator to what, to transform your time series data to the frequency one. But in our cases, in the convolutional neural network, we can use the sharpened image or the filter kernel, right? And so, but this is the specialized filter to represent your data to time series to the frequency one. But in convolutional neural network, we may have learned pattern in order to what? In order to provide or satisfy these conditions. Okay? This is how we can convert this term to another one. And so this is just simple matrix multiplication like this one. X is a convertible vector, and w, n times w, can be what? Multiplied with xt, and so this pattern represents the frequency characteristic, just like the convolutional neural network. But convolutional neural network has the learnable kernel, but this kernel is fixed, right? This is so simple. No, CNN learns this kernel function for your dataset or with respect to your dataset. But this convolutional operator enable us to time series data to the frequency one. Okay? But in convolutional neural network, we have the same procedure like this one. Always the same. But this fixed convolution, fixed kernel. Right? Do you understand what I'm saying in here? This is simple. Don't be afraid about the integral. This is just the what in discrete form. We have the sum matrix, kernel matrix in here, and this matrix multiply with the x, and then we will get the x f values, frequency values. This is transformation. Okay? But how can we represent this form in here? In matrix multiplication form, x wn times xt can be given in here, and so this w is represented by the w0, 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 and w0, w1, w2, w3, and w0, w2, w4, w6, and goes like this way. Okay? w0, w3, w6, w9. Okay? And so this small w is equal to what? Exponential over 2 pi j divided by total n. Okay? And so this creates the what in, for example, with the amplitude form of this one, 4, and we may have this pattern like this one. For example, 1, 1, 1, 1, because the over 0 creates the 0 value in here, and 1 minus 1 and minus 1 and j, this is the imaginary part of your code, and 1 minus 1, 1 minus 1 and 1, j minus 1 and j is given here. And so this matrix is calculated from the what? From this vector. And so if we have this matrix, and then we can multiply this xt, and this matrix creates the frequency characteristics of our code. Okay? This is simple. Just like that. There is no another information about the Fourier transform. Be sure about that. I will show you. Be patient. God damn it. Okay. Yes. In the second example of our code, we will continue with the what? The your 0, 1 Fourier transform. Okay, dot pi. Okay, and so as always with you, we need to import the numpy as mp and import matplotlib dot py plot as plt. Okay, and so we need to create some function definition in here, like this one, the function definition. Okay, and so def the create signal time points must be given in here, and so this signal can be created with the two values of sinus and cosinus, 300 times 2 times mp pi times and time points. I selected 300 because the Fourier transform generate this value as a 1 values. Okay, and so if we apply the Fourier transform to this signal, and then we will get the 300 values with amplitude of what? 1. Okay, this is the specific example. And also we can give the another function with the cosinus and 100, for example. It's arbitrary number. And def plot time series can be given in here, like this one, the signal and time points, and title can be given in here. And so plt plot time points and signal in the y-axis, plt title is equal to the title, and plt x label is equal to the time sec, and y is equal to amplitude. Okay, So PLT grid true, and then we can create the discrete Fourier transform. Signal and sampling frequency must be given in here, like this one. Normally you have some prepared library to calculate this function, but we can create the some kernel matrix or the convolutional matrix to represent the R code. Okay, and so you can easily use this code in the real-time application or any other, for example, embedded system. Okay, N is the length of the signal, K is the MP arrange with the N, and K reshape function with the N times 1 vector values in here, and W is our matrix MP exp minus 2 J times MP pi times K times N divided by N. This is the creation of this matrix. Okay, it's simple. After that, the frequency of the K times sampling frequency divided by N. Because we have the specific sampling frequency in here, we need to scale it, right? Q and C's, this, and then frequencies can be returned, and MP dot W and signal. This is the this is the Fourier transform, right? W multiply with the signal. That's all. Okay. So def plot discrete Fourier transform in here with the signal and sampling frequency and the title. Okay, and so frequency and Fourier transform is equal to what? These terms, right? This is the calculation of the what? This one. And after that, you may need to know this frequency in this right now, because the detailed information about the frequency domain in mathematical formation. Don't worry about this information, and we should bound the frequency representation in here like this one, because we have the 500 values in the sampling frequency, because if we choose the sampling frequency 1000, and we can generate the values at the or the upper limits of this frequency is the half of the 1000, which means that 500. Nyquist theorem, right? Do you remember that, the Nyquist theorem? Okay. If you don't worry about that. It's not our concern in this lesson. PLT plot is given in the frequencies with the positive frequency in these. Okay, and also we should give the MP abstract values with the Fourier transform with the positive frequency in this, right? Just need to draw these values, only these values. Okay, and after that we have this information. PLT title must be given with the title, and PLT X label should be equal to the frequency in the time of the hertz, PLT Y label is the what? The amplitude. Okay? And also PLT grid must be given. Okay. And then the main code starts in here. Main code. So the sampling frequency can be assigned to 1000 hertz. Okay, and so we will get the information up to what? The 500 hertz, according to what? The Nyquist theorem. Okay, and so the time points can be created to what? The MP arrange function with the what? 0 to 1 second and 1 divided by sampling frequency. Okay, and so we have the what? The 1 divided by sampling frequency data on the period of the what? The 0 to 1 seconds, right? So the signal can be create the signal in here with time points, and after that PLT figure fixed size 12.8 and PLT subplot 2, 1 and 1, and plot time series signal with what? The signal, time points and the time series data. Okay, and PLT subplot is 2, 1, 2. The second row is assigned, and so the plot discrete Fourier transform with the what? The signal, sampling frequency and DFT. Okay, up to 500 hertz. After that, the PLT tight layout and PLT show must be given in here. And so, if I run this code, I'm sorry, I've been some mistakes in here. Time points, the time points 0, 1 and 1 sampling frequencies, and this is 100. Okay, that's the problem of this code. This is also true. This is also true. Oops. No. No. K times sampling frequency, yes. MP dot, yes. Frequency, yes. Signal sample frequency. Frequencies, freaking this, and positive frequencies, yes. This is also true. Okay. What about time points? MP arrange 0, 1. Signal, time points, yes. Signal, sampling frequency, yes. Plot time series is wrong in here. Okay. Time points 2 MP times time points plus MP cos time points. We must return the signal. So, okay, just see that we have the time series data in here like this one, but we have the 100 values peak At what? At the amplitude of 500. And we have the 300 values in the what? The 500. It's an arbitrary number for the amplitude, but just see that the upside signal is transformed into the what? Into meaningful data. Which means that in your neural network application, you may not utilize this kind of signal, maybe, because we have in here like this one's the 1000 data. But if we take the some window or the pattern in here and convert into this one, this is more meaningful, right? So in Fourier series, we can generate from the 1 signal to the 1000 signal. In the Fourier transform, we can take the 1000 data into the 2 meaningful parameters, right? You get it? Okay. And so this must be changed with the what? For example, we can assign to what the 10 hertz and what 200 hertz. And so if I run this code, and this code is generate the what? This pattern, but this is the what? 20, I think. And so this is what? 200, right? 10. Because this is 10, okay? Do you understand the utilization of this code? And so this is the basic representation of discrete Fourier transform. And so if you want to define this term like this one, and so you can easily arrange this code or manipulate this code into the what? Into any microcontroller or any signal or any projects, okay? Okay, and so if you want to train this network in here, you may utilize the many neurons, because we have some unknown pattern in here. But if you take the Fourier transform and you get this information, okay, and so I can deduce that there may be a sinus signal and cosinus signal to represent the R signal. And so this is easy to get the information of the some patterns, 10 hertz and 200 hertz. And we want to use this signal term or frequency term to generate the sinus and cosinus signal, because it's a periodical signal. But if you put the neural network to these terms like this one, and so your neural network may be forced to learn this pattern. But in the second case, it's so simple and useful, right? Okay? Okay. Let's take a 5 minutes break, and then we will continue with another transformation techniques.